Okay, ma'am. Morning. Let me start the class now. So, in our previous class, we were seeing our second module. And then we have completed the portions in the second module. We'll pass on to the next module now. So, our next module is dealing with the constant area duct. Let me go to the presentation. So, I hope my voice is audible. So, our third module is dealing with flow through constant area duct. In our previous module, we were seeing a variable area duct. So, in constant area duct, in variable area duct, we call it as flow through variable area duct. We call it as isentropic flow. Here, flow through constant area duct, we'll call it as two types of flow. One is called fanno flow. Another one is called Rayleigh flow. So that means it is flow model. Call it as the isentropic flow model, fanno flow model, and Rayleigh flow model. That means immediately we can understand. So each flow is different on its own way of having equations and also the properties. Okay, so that means each flow model can be applied for particular applications. So, for example, isentropic flow model, that is flow through variable area depth, can be applied for a nozzles. So, like that, this fanno flow and Rayleigh flow can be applied for a constant area depth. So, what is constant area depth? It is very clear, obviously. So, it will be having a uniform flow area, either it may be a circular or non-circular, whatever it may be. So here, in this case, again, there are two types called fanno flow and Rayleigh flow. What is the difference? So if it is a fanno flow, we call it as flow in a constant area duct without heat transfer with friction. Such a flow we call it as a fanno flow. In Rayleigh flow, will not consider friction, will consider heat transfer. So where such flow model will be applied in the real engineering applications. To take designing of air conditioning duct, you will see that any centralized air conditioning system will have a common cooling system. Air will be cooled in a common place. We'll have a centralized refrigeration system. We'll cool the air, and that will be supplied through the various places through a duct only. We might have seen it in all the large malls and theaters and all. Generally, we'll be using uh, this centralized air conditioning system. If you see that the duct, when the cold air is passing through that, it is very important. The duct should be properly insulated, correct? Otherwise, there will be heat loss. And then, when the air is flowing over the duct, there will be some wall friction will be there. So, in the design of air conditioning duct, the insulation of duct and frictional loss is a major consideration. So in that case, we can apply this flow model. So we call it as a fanno flow model. The name fanno who developed this flow model, and it is being applied for all the constant area duct here. So without heat transfer in the sense, no heat interaction to the surroundings. That means it is completely insulated and wall friction is considered. Okay. Now, what are all the governing equations here? So for this, we'll use a continuity equation and also our adiabatic energy equation. Using adiabatic energy equation, adiabatic energy equation here also it is applicable. H naught equal to H plus of C square. And also we can use continuity equation. Okay, by using continuity equation, these are all the governing equations. By using continuity equation, m dot equal to rho AC. Since the area is constant here, so in Fanno and Rayleigh flow model, we take mass flow rate per unit area always, and we'll write it this way. This m dot by A, we'll refer it with a notation called G. We call it as a mass flow density. Generally, we used to refer this m dot by A, the G. So we'll write capital G equal to rho into C. Now coming to this expression here, I can, if I'm writing C equal to, from this previous one, the above step, I can write C equal to G by rho. I'm substituting, I'll take this as equation number 1. Substituting C in 1, then we can have H naught equal to H plus of G square by rho square. So generally we'll use this expression for Fanno flow as well as in another flow called Rayleigh flow here. So this is the generally the governing equation. We'll use it for Fanno flow model. And this Fanno flow process can be represented in a small plot here. So let me first explain that one. Take this. So here we are saying that the Fanno flow curve or Fanno flow process, which is represented in the enthalpy entropy diagram. Okay. So in this, we have the expression, the governing equation just now we have obtained. Okay, H naught equal to H plus G square by 2 rho square. So that equation is applicable here. And if you see this curve here, uh, we all know that there are two types of flow, subsonic flow and supersonic flow. When the m is less than 1, we call it as subsonic flow, and m is greater than 1, we call it as a supersonic flow. So if you see this diagram here, we have a curve which represents the Fanno flow process. We call it as a Fanno line or Fanno curve. Suppose if it is a subsonic flow, the process will be taking place from A to F. If it is a supersonic flow, the process will be taking from B to F. That means what? What we can understand from this? For example, suppose if the flow at the entry of a constant area duct, the flow is subsonic. Okay, so what will happen? The flow properties, that is the Mach number, will increase from subsonic to the sonic, m equal to 1 here. Maximum it can go up to 1. After that, if it goes, so what happens? You see it here, the entropy is decreasing. Here the entropy is increasing to this point. When you are allowing the Mach number to go beyond 1, from less than 1 to the greater than 1, so the entropy is decreasing, correct? If you see this curve here. So according to the thermodynamics, the entropy will never decrease in the real process. So that is not possible. Entropy may constant maximum, that is ideal. Always entropy will increase in all the real processes. So there is no possibility of decrease in entropy. That means we can understand here uh, there is no possibility of Mach number to increase from the that means Mach number will not go beyond 1 when it is less than 1. That we have to understand it here. Next, on the other hand, suppose if the flow is supersonic at the entry, what will happen? The Mach number will decrease and it will decrease up to the 1 from greater than 1 to maximum it can go up to 1. After that, if you are allowing it to go, if you are allowing it to decrease the Mach number less than 1, that is not possible in the supersonic flow case. Again, your entropy is decreasing here. If you are allowing the Mach number go less than 1 for the supersonic flow here. So here also there is no possibility of decrease in entropy. So that means suppose if the flow is supersonic, maximum the flow can be reduced to a sonic flow conditions. So that means, so here we can understand this, the point F, we can call it as a limiting point for the fanno flow process. If it is a subsonic flow, maximum it can go to sonic. If it is a supersonic flow, maximum it can decrease up to sonic here. So that is the important point that we have to understand it here. So the sonic point m equal to 1. So already we know at the sonic point, all the properties are called critical properties. So that means at the limiting state, we call it as a critical state. That is P equal to P star, T equal to T star. So everything that we need to understand it here. So that is very, very important with respect to the fanno flow here. Okay. Now, let us understand this, the property variation with respect to the fanno flow here. Yes, I hope the diagram is visible to all. Now, this is a constant area duct. We have taken two sections, 1 and 2, where the Mach number is m1 and m2. And we have a limiting state where the point F, you have seen it here. That point m equal to 1 here. That means what we have understood here, that if the flow is subsonic, maximum the flow can the flow Mach number can be reduced maximum up to m equal to 1 here. So that we can able to see it here. That means if I am having a indefinite length of the duct, maximum the flow can be reduced to Mach number m equal to 1 if the flow is subsonic. I mean increase to Mach number 1, the flow is subsonic. And if suppose if the entry is supersonic, the Mach number can be reduced to 1 if I am having infinite length. That's why we have put it as maximum length, L1 max. You see it here. L1 max means maximum possible length, indefinite length. Even if I am having, the Mach number cannot be allowed to go beyond 1 on either case, if it is a subsonic flow or supersonic flow here. So suppose if you see it here, that's what we are referred, it is L1 max, and from 2 it is L2 max. So that means this is for an ideal condition. This is for what is an actual condition. There are two sections. I have taken two sections. So from this I can able to get my actual length of the duct. From this I can able to get the actual length of the duct. That means by using this ideal case of L1 max and L2 max, so we have the possibility of designing the some of the physical properties. That is one physical properties or physical dimension is length here. Okay, actual length of the duct. So that we need to understand with respect to the fanno flow here. And coming to the property variation. So if you see it here, this is the control volume and this is the control surface here. With respect to that, the variation has been defined. With respect to the static properties, it is going to change, obviously. Okay, and it is a wall friction is there. Because of the wall friction, there will be a change in entropy there. So that means you see it here, the process has become real. Since we use adiabatic energy equation here, See it here, since we use adiabatic energy equation, H naught equal to constant. Since adiabatic energy equation is applicable for this flow model, H naught equal to constant. H naught equal to constant means H naught equal to Cp into T naught. So what we can write, this is again constant here. So for the two section, if I am writing, can write Cp equal to T naught 1 and Cp equal to T naught 2. If I am writing this one, if I am writing H naught 1 equal to H naught 2. So I can cancel this Cp. I can write T naught 1 equal to T naught 2. That means the fan of flow stagnation temperature remains constant. Since friction is involved, hmm, since wall friction is involved here, since friction is considered, P naught 1 not equal to P naught 2. Stagnation pressure varies. So that we have to understand it here. So in our previous flow model, isentropic flow model, it is a variable area duct. Stagnation temperature and stagnation pressures are constant. Because of a fan flow model, it is a constant area duct. Stagnation temperature remains constant and stagnation pressure varies. No friction is considered, so that stagnation pressure will not be changing here. Okay. Okay. So this is all about the theoretical concepts that we need to understand with respect to the fan flow process here. So like in our gas tables, we use a isentropic table. So in the fan flow also, we have the fan flow table is there for solving the problems on fan flow here. Okay. So that we are going to use it, our fan flow table for solving the problems of fan flow. And from this diagram, we can write L1 max and L2 max. This difference is going to give the L here. That means if we want to get L, we can write L1 max minus okay. So this is in all our gas dynamics parameter, we used to make it as non-dimensional. So what we'll do, we'll consider the friction factor here, and we'll make it as a relation called 4F by T. Okay. In fluid mechanics, you might have studied. That is a friction factor. So this is nothing but your friction factor because we consider the friction here. So by considering this one, we are making this L also in non-dimensional. So I am just multiplying this so that I can write 4FL by D, 4F L1 max by D minus, because diameter is constant, 4F L2 max by D. So this is dimensional, this is non-dimensional because F is no unit friction factor and L is in meter, D is in meter. So both gets cancelled. We will get in a non-dimensional parameter here. So this parameter is also available in our fan flow table corresponding to the Mach number, like our stagnation pressure ratio, stagnation temperature ratio, and in addition to that, we'll be having this 4F L max by D, L1 max and L2 max. If I'm taking it for M1, it is L1 max. If I'm taking it for M2, that is at section 2, we'll consider it as 4F L2 max by D. No area ratio will be there because the area is constant here. Okay. So let us just look into the our gas tables for the fan of flow. As you can see, flow of perfect gases with friction. We have gamma equal to 1.3, 1.4, and 1.67. Suppose if I'm taking at page number 75. This is our fan of flow table. So we have the expression for P by P star, C by C star or rho star by rho, and T by T star. Stagnation pressure ratio will be there. Since stagnation temperature is constant, we are not using that one. And impulse function is there. And you have this 4F L max by D. So that also available. So we are going to make use of these expressions to solve the fan of flow problems here. Okay. So one thing we need to understand here, this P star and T star and all, it refers at Mach number equal to 1 here. Right? It refers at the limiting state m equal to the limit m equal to 1 is the limiting state for fan of flow. In unlike in our isentropic flow, we never call it as a limiting state in the isentropic flow. It is an intermediate state between the subsonic and supersonic, because the flow may change from subsonic to the supersonic, and also supersonic to the subsonic in reverse. But here it is not possible. If it is in subsonic, the Mach number may increase up to 1, and if it is a supersonic, the Mach number decrease may maximum go up to 1. That's why we call it as m equal to 1 as a limiting state. At limiting state, we call T equal to T star, P equal to P star, C equal to C star, etc. Like that we can write it. So that means, so when we write this ratio, you see here the gas tables, when we write this ratio, suppose for example, if I'm getting P by P star, that means M equal to M1 equal to 0.1 I'm taking. So I'll write, suppose for example, I'll write this from gas tables. Okay, fan of flow table. For M1 equal to, I'm writing 0.1. For M1 equal to 0.1, I'll write P1 by P1 star equal to, what is the value? 10.716. Okay. I'm having another value M2. M2 equal to 0.2. For this, I'm having the P2 by P2 star. P2 by P2 star is 5.346. So this one, what we'll write, this can be written it as either P1 by P1 star, or this can be written it as P simply P1 by P star. No need of using this one here. The reason, there is only one limiting state is there. Even if it is a T1 star and T2 star, both are same. Both are at M equal to 1 only. So there is no meaning of mentioning P1 star or P2 star or T1 P2 T1 star or P2. Both are same. T1 star or T2 star here. Okay. So that means, so whenever we use the limiting condition, properties at limiting condition, we use to specify just with the asterisk of star only. P2 by P star. 5.346. Okay, that we need to understand. Even if you write P1 by P1 star, that is also right. If you simply write P star, that is also right, because asterisk is this star limiting state is only one point only. We don't have a T1 star and P1 star, T1 star or T2 star. So that we need to understand it here when we're solving the problems. Okay. So this is the basic idea. We'll go to the problems on fan of flow. Okay. Any doubt in this, my dear most friends? Any doubt in this fan of flow? Okay. See that any clarification you need for solving the problems on fan of flow, understanding these basics of fan of flow. We need to understand that we have the limiting state for the fan of flow. So if it is a subsonic flow, maximum it can go up to 1. If it is a supersonic, the Mach number may decrease, it may go up to 1. That's all. At limiting state, we call it as a critical, because M equal to 1, all properties are critical properties. Okay. That's all. Okay. So this I can go to the problems on fan flow. Okay. So let me see this fan flow problems now. Okay, so let me read this problem now. The Mach number and insulated constant area duct increases from zero point 0.3 to zero point 0.7 because of the friction. The initial pressure is 200 kilopascal. Determine the fluid pressure as the determine the final pressure as the duct is 150 mm diameter. Smooth steel friction factor is given as F equal to 0.008. Determine the length of the duct for gamma equal to 1.4. Also determine the maximum possible with the same initial conditions. Maximum possible length with the same initial conditions. So that means in no problem it will be specified as isentropic flow, fan flow, or other types of flow. They will never specify. With respect to some keywords, we have to understand the particular flow model. So a friction factor will be coming only in the fan flow. Okay. Constant area duct is also there, but we have another flow called Rayleigh flow, which you are going to see it later. So that is also a constant area duct. There we won't have friction. So if it is a constant area duct with friction, we can call it as a fan flow. Okay. So this is the data we have it. So now we'll proceed with this. Okay. So if you see here, they given the Mach number value, that is M1 to 0.3 to 0.7. One thing we need to see it here, if the Mach number is less than 1 in a particular problem, that is M1 at section 1. At section 2, the Mach number will never go greater than 1. Maximum it can go up to 1 because we have a limiting state. You see it here, 0.3 to 0.7, maximum it can go up to 1. In the same manner, if the Mach number is greater than 1 in any problem, it will not go on the other side of the 1. So that means Mach number may decrease, it may go up to 1. So that we need to understand. So M1 and M2 will never be less than 1 or greater than 1 in the same problem. Okay, with respect to the fan flow. So the initial pressure is given as 200 kilopascal. We have to find out the final pressure here. With the friction factor values, we have to take it, and also the gamma is 1.4. Now what we'll do, we have a relation L equal to, so in this way we can represent this a constant area duct. Section 1 and 2 can be represented. From 1 I can take, from 1 to the limiting state I can call it as L1 max, maximum length. From 2 to limiting state I can call it as L2 max. So the difference will be giving us the L here. So that L we need to find out here. This L1 max and L2 max for ideal condition. L is the actual condition. Actual designing of duct will be getting it. So from this I can write L equal to L1 max minus L2 max. So multiplying this by 4f by d, I can write 4fl by d equal to 4f L1 max by d minus 4f L2 max by d here. Okay. So with this, the given data, we have it. M1 is 0.3 and M2 is 0.7. Diameter is 150 mm. Friction factor is 0.008. And initial pressure is 200 kilopascal. Now we have to refer our gas tables for getting the other the property values, the property ratios. Proceed with the problem. The idea is we need to find out the first L here. So what we'll do, we'll get our fan flow table. We'll take gamma equal to 1.4. Gamma is 1.4. M is 0.3 first. So M is 0.3. Okay. So for M equal to 0.3, we are taking, we need pressure and L. So I'm taking these two parameters, 4f L1 max by D equal to 5.299. So you see here 5.299. And we are taking the P by P star 3.619. So it is 3.619 here. So we can write either this P1 by P star or P1 by P1 star. Both are right, as we discussed now. Now what we'll do, we have been given P1 here. So we'll substitute this P1. So we'll get P star. Later we'll use it to get our P2. What we'll do, we'll take M2 equal to 0.7. We'll get P2 by P star. Knowing this P star, I can able to get the P2 easily. So in that way, we are going to proceed it. For M2 equal to 0.7, we'll refer our gas tables. M2 equal to 0.7. We are getting 4F L max by D and also P by P star. For 0.7, it is 0.208. That is 0.208. And for P2 by P star is 1.493. It is 1.493. So for this, we have P star, and what we'll do, I will substitute this P star here, 55.263 that we have substituted here, and we got our P2 as 82.507 kilopascal. Okay, because we have substituted this P is in kilopascal, so that we are getting P2 as in kilopascal. Now we need to get our L here. For getting this L, we are going to use the expression 4F L by D equal to 4F L1 max by D minus 4F L2 max by D. So both we have got it. So we are going to substitute this 5.299 minus 0.208. This one 4F2 L max. So friction factor has been given. Diameter is also given here. So let us substitute this F and D value here. F is 0.008 and D is 150 mm. This is 0.15 meters. So we'll get our L as 5.019. And also they are asking us to find out the maximum possible length. So in this, what is the maximum possible length here? L1 max is the maximum possible length. L2 max is smaller than L1 max. L is also smaller than L1 max. So L1 max is the maximum length here. So we need to get L1 max. So for this, what we'll do, we'll write this expression 4F L1 max by D, so that already we have got it. Okay. So knowing our F and D here, substituting those values, we'll get our L1 max as 24.839 meters. So we have calculated final pressure, length of the duct, and L1 max. That means we can understand. So we got the physical dimension. This is the designing of duct, physical dimension with the ideal condition of L1 max and L2 max. L1 max and L2 max is ideal condition. So what is the meaning of this 24.839? If I am allowing the Mach number is 0.3 initially, if I am allowing the flow to take place for a length of 24.8 meters, the Mach number may go up to 1. From 0.3 to 1. So that is the meaning. For the Mach number to get m equal to 1, I need to allow the flow to take place for a length of 24.83 meters. That's what it says in this diagram. You see it here. So I need to, for getting a limiting state here, I need to allow the flow to take place from 0 meter to 24.9 meters for this case. So this is an ideal case. By using this ideal case, we are getting our actual length we need it. Okay. I hope you understood this problem. Any doubt in this, my dear friends? I hope I can proceed it. Next, we'll have another problem. An insulated pipe of 400 meter long, 73 Arma, 73 are
Attendance சொல்லும்போது இன்ஜின் சார்
73 are
நான் தான் சார் நசீம் அஃசல் சார்
Naseem Afzal. Yes sir, இதோட
எஸ்
சீக்கிரமா
சார்
ஜாயின் பண்ண முடியாது சார்.
சார் இல்லை சார் நான் ட்ரெயினில் இருக்கேன் சார் அதனால
நீங்க
ஜாயின் பண்ண லேட் ஆயிடுச்சு சார்
நீங்க
இப்போ தான்
ட்ரெயின்ல
சார்
இருந்தா
ஜாயின் பண்ணேன்
லீவ் ஆயிடுங்க சார். ட்ரெயின்ல ஏன் சார் டிஸ்டர்ப் பண்ணிட்டு இருக்கு? ட்ரெயினை டிஸ்டர்ப் பண்ணாதீங்க சார்.
சார் ட்ரெயினெல்லாம் டிஸ்டர்ப் பண்ணல சார் நான் பாட்டு அமைதியாக உட்காந்து காமிச்சிட்டு
இல்லம்மா, நம்ம கிளாஸ் எடுத்தா
சார்
ட்ரெயினை
நானும்
டிஸ்டர்ப் பண்ணாதீங்க.
ட்ரெயின்ல தான் சார் இருக்கேன். மக்கள் லேட்டா ஜாயின் பண்றான்.
அதான் ட்ரெயின்ல நம்ம கிளாஸ் எடுத்தா ட்ரெயின் டிஸ்டர்ப் ஆகுமே கண்ணா. ஓகேவா? என்ன நசீம் அப்சல். Okay, so we'll see our second problem. An insulated pipe of 400 meter long, for which the friction factor is 0.005, is used for supplying compressed air. The air temperature and pressure at the inlet are 35 degrees Celsius and 9 bar, and the inlet Mach number is 0.1. If the diameter of the pipe is 15 centimeter, calculate the air flow rate, velocity, Mach number, pressure and temperature at the delivery end of the pipe. Consider the environmental pressure as 1 bar. Okay. So here immediately we can understand this is a fan of flow problem. The reason we have uh, length of the constant area duct, and it is a you see that friction factor is given 0.005. Okay. So that we will write the given data here. Length is 400 meter, friction factor is 0.005, and initial temperature is 35 degrees Celsius. Okay, and you see it here. The Mach number M1 is 0.1 here, and diameter is 15 centimeter, and they are given it as environmental pressure. That means outside condition. So for this, we need to find out the airflow rate, velocity, Mach number, pressure, and temperature at the delivery end of the pipe. Okay. So for M1 equal to 0.1, first let us get the this parameters P by P star, T by T star, and 4F L max by D for the fan of flow. So we'll get for M equal to 0.1, P by P star is 10.943, 10.943, and T by T star is 1.197, and 4F L max by D is 66.922. 1.197 and 66.922. Knowing our P1 and T1, which are given here, we'll get our P star and T star. So then this will be later used to find out the P2 and T2 here. And also we can write this expression 4F L1 max by D, knowing F and D as 0.005 and D is 0.15, and L1 max will get as 501.9 meters. So writing the expression of L equal to L1 max minus L2 max here, we need to find out the exit properties. Am I right? So what we'll do, we'll try to find out the any one of the exit, any one of the parameters that are related to the exit here. So that we'll get the Mach number M2, either P2 by P star or these ratios or 4F L2 max by D. By having this relation with us, we know L and we know L1 max, correct? So that we have the possibility of finding the L. Okay. So that we can easily go to the exit, we can easily get our exit properties. So L2 max, if you know, I'll get 4F L2 max by D. From this, I'll get M2. So in all our problems, we used to get any one of the properties easily, then we'll get the rest. So that is the usual way we'll proceed with the gas dynamics problems. So if you see it here, we have L1 max, this is 501.991 meter. So we have the relation L equal to L1 max minus L2 max. So I can write L2 max equal to L1 max minus L here with this relation. Already we know L1 max, and also L is also L also we know. From this I will get L2 max. Knowing L2 max, what I can do, I can get a relation of 4F L2 max by D. I can, though there I can substitute my L2 max. 4 into F is 0.005, L2 max is 101.915, and D is 0.15. That will substitute it here. So what we'll do now, we'll refer our gas tables corresponding to that. What is the value of M? So that we'll get it. So 4F L2 max by D is 13.588. Okay. So that we'll search it in our gas tables. You see it here. 14 is that, 18 is that. So you see it here. Our value is 13.558. So we can either you can take the average of this one, or we can take this as 0.2. Either it may be 0.19 or M2 as 0.2 here. So that we'll get our M2 as 0.2. One thing we need to remember, whenever we use this 4F L max by D, we'll get the two values for the same 4F L max by D. One will be Mach number less than 1, one will be Mach number greater than 1. Because this is for both subsonic and supersonic. So now we have the one thing we need to see that in the initial Mach number is less than 1, our final Mach number should also be less than 1. If you search in the gas tables now, 4F L max by D, around this 14 will be having in another place where the Mach number will be greater than 1. That we should not take it, because our initial Mach number is less than 1, our final Mach number should also be less than 1. So in that sense, we are going to take the less than 1 Mach number value of M2 equal to 0.2 here. Now it is easy for us to get the rest of the values. So P2 by P star and T2 by T star, 5.455 and 1.190. 5.455, 1.190. Already we know that P star and T star here, so that we can substitute it here. We can substitute it here, those P star and T star. So P2 equal to 5.455 into P star is 0.8224. So we'll get our P2 as 4.486. And coming to the temperature ratio, this is 1.190 into T star, which is 257.3099. So we'll get our T2 as 306.18 Kelvin. Okay. And we have been asked to calculate the flow rate also. Okay. So for this, again, if you refer our gas tables, we have a velocity ratio is that C by C star. So for this, we have M1 equal to 0.1. We can take C by C star is 0.109. So that we will take it. So what we will do, we'll get our A1 here. A1 equal to, other relations are same. Acoustic velocity of sound will be having the same relation. A1 equal to root of gamma or T1. Gamma is 1.4, R is 287, and T1 is 308 Kelvin. So 351.78. Knowing our A1, we can get our C1 here. C1 equal to M1 into A1. M1 is 0.1, A1 is 351.78 here. So from this, we'll get our C star. Knowing our C star here, again go back to our fanno flow table. For M2 equal to 0.8, we'll get 0.218. So for this M2 equal to 0.2, we are getting C2 by C2 star as 0.218, where that C2 will get it because we have calculated C star and also C1. So C2 equal to this is 0.218 into 322.74. C2 will be 70.357. Okay. So we need to find out the mass flow rate. So mass flow rate, what is mass flow rate expression? M dot equal to rho AC, rho 1 A1 C1 equal to rho 2 A2 C2 here, since mass flow rate remains constant. And we know that rho equal to P by RT, and this is circular area, so pi by 4 D square, and C2 we know that. Even if you write rho 1 A1 C1, that is also right. Okay, because area is constant here, A1 equal to A2. Any relation you can use it, you will get the same for the with respect to the mass flow rate here. So P2 is 4.486 into 10 power 5 Newton per meter square. R is 287. T2 is 306.108, which we calculated already. Diameter is given, and C2 here calculated just now 70.357. So we'll get our mass flow rate as 6.346 kg per second. Okay. So in this problem, we have been asked to calculate the exit properties as well as the mass flow rate. Exit properties as well as mass flow rate, so that we have comfortably calculated and also easily calculated using our gas tables. Using our gas tables, the problem solving has been very much simplified in the case of gas dynamics. Idea is we need to know the basic equations. We need to know how to use the gas tables. That is very important. I hope, my dear friends, you understood this. You see that any doubt you are having, you just ask me. I'll just show you, and also you can take screenshot of this one, whatever we discussed. Screenshot எடுத்துக்கங்கமா. Friends, please solve. So coming to the problem. First problem. The end of the first problem. And coming to that second problem. Hope you noted. So whatever we discussed today. See that just go through that. You have any doubts so that I can clarify now itself using of gas tables, using of any equations. Just see that I wait for some time. That I take attendance. Okay, my dear most friends, let me close my presentation now. This I hope are clear for today's class. Let me take up next. Attendance answer building mark. 10.
Present, sir.
Rashid.
10 present, sir.
Yes. 12.
Sir, yes, sir, present, sir.
Shreya. 33. 33. 1060.
Hello, sir.
Hello sir, சொல்லுங்க சார்.
Hello, sir.
ஹலோ சார், சொல்லுங்க சார்.
Sir,
சொல்லுங்க சார். ஹலோ சார். 1060. லோகேஷ்வர்.
hello, sir.
எஸ் சார்,
Sir,
ஹலோ சார். எஸ் சார், ஹலோ சார், சொல்லுங்க சார்.
present, sir.
ஓகே
I
சார்.
can't hear.
1076.
Hello, sir.
ஹலோ சார், ஓகே சார், நோட் பண்ணிட்டேன் சார்.
Okay.
1076. ஷாகுல் அமீன்.
Sir, present, sir. Present.
இல்லை எங்க சார் எல்லாம் இதில் இருக்கீங்களா சார்?
Sorry, sir.
ட்ரெயின் ஓட்டிட்டு இருக்கீங்களா சார்?
Sir. ரொம்ப சத்தமா இருக்கு சார். ஏர்போர்ட் கூட இல்ல. நதிங் மக்கள் கூட என்னதான் சார் இருக்கு. கேட்டு இருக்கேன். Yes,
இண்டிவிஜுவல்
sir.
லாகின்
73
பண்ணணும்.
okay, sir.
இண்டிவிஜுவலாக லாகின் பண்ணணும்.
Sir,
இண்டிவிஜுவலா லாகின் பண்ணணும் 76%.
சார் கவர் இல்ல சார் போன்ல, அதனால சார்.
கவர் கவர் இல்லாம ஒரு கிளாஸ் எதுக்கு அகாடமிக் அட்டன் பண்றீங்களா? அதெல்லாம் கிடையாது. கிளாஸ் லாகின் 76% அவ்வளவுதான். ஓகேவா? உன்னோட அட்டெண்டன்ஸ் முடிஞ்சு போச்சு, விட்டுரு. அவ்வளவுதான். ஓகே
சார் இப்போ லாகின் பண்ண முடியாது பார்க்கவா சார்?
76% அவ்வளவுதான், முடிஞ்சது, நீ விட்டுரு.
ஓகே சார். சார் 76 சார்.
நீ 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 லீவ் ஆகிக்க, அவ்வளவுதான். அட்டெண்டன்ஸ் போட்டேன் உனக்கு 76 போலாம்.
ஓகே சார், தேங்க்யூ ஸோ மச் சார்.